Okay, so today we're starting 5.4, but before we get into the notes here, we just took the fill in the blank quiz, and then starting tomorrow, we're going to do something like this. So if you want to take a, let me change the color so it matches better. You can take a screenshot of this or take a picture of it. Take a selfie of it. Yeah, there we go. So tomorrow, I just wrote out some random sine and cosines and some random angles. That's what they all are. So pick any angle from the unit circle, pick sine or cosine tomorrow only. You'll have 10 of these in 10 minutes. So that's a lot of time. How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8. Let's just add 2 more. Let's do a sine of 2 pi. Okay. And then cosine of let's see, I'm trying to 3 pi fourths. How about that? Okay, so there's 10 of them.
Some of them. I believe the cosine of pi.
We'll go through them. Let's just practice for tomorrow. That's a lot of time. 10 minutes, twice as long as what it just took you to fill it in. But what's going to happen is on Wednesday we're going to do 10 of them in 10 minutes, but it's all 6 trig functions, and we'll practice that tomorrow too. But then after that, after we do all 6 and 10 on Wednesday, then we do all 6 every time, and the time gets shorter and shorter and shorter and shorter, so that you become more and more proficient. Okay, so let's go ahead and do these. Cosine of 5 pi fourths, and I'll talk you through again the way I do it. When I see that, I think pi fourths first, which is square root of 2 halves, square root of 2 halves all the time. 5 fourths, I look at the numbers. 5 fourths is a little bit bigger than 1, right? So that's a little bit bigger than pi. A little bit bigger than pi rotates into quadrant 3, where both the x and y are what? Negative. Cosine is the x coordinate there. So the answer is negative square root of 2 over 2. Done. Okay. Cosine of 11 pi 6. I hear the pi 6. And when I hear pi 6, I think square root of 3 halves, comma, 1 half. I know 11/6 is in quadrant 4, where cosine is positive because x is positive. So the answer should be positive square root of 3 over 2. Sine of pi. Pi is a quadrantal angle. It's over here at 180 degrees. What's the sine value there? Well, what's the ordered pair at pi? -1, comma 0. On the x-axis, the sine value is always 0 because sine y height. Well, that didn't sound right, did it? Sine y height. There we go. All right, cosine of pi halves. Pi halves is another quadrantal angle. It's straight up at 90 degrees. The ordered pair there is 0, comma 1. Cosine is the x coordinate. It is also 0. Yep. 7 pi fourths. I hear pi fourths. I know that's your 45-degree reference angle, pi fourths reference angle. That's in quadrant 4 because 7 is 1 less than twice the denominator. And I know that the ordered pair there then is positive square root of 2 halves, negative square root of 2 halves. Positive, negative. Sine y height. So it should be negative square root of 2 halves. And by the way, when we take these quizzes, it's either all right or all wrong. Right? If someone just says, oh, I just forgot the sign. Yeah, you got the opposite of the wrong answer. That's like the most wrong you could be, right? Opposite of the right answer. 180 degrees away. Pi radians away. All right, cosine of 5 pi thirds. 5 pi thirds. Pi thirds is 1 half square root of 3 halves. Any 1/3 is pi 1 half. Any pi thirds is 1 half comma square root of 3 halves. 5/3 is in quadrant 4 because 5 is 1 less than twice the denominator. And in quadrant 4, again, it's positive, negative. So the cosine there is the positive x value, which is a half. Okay. Sine of 2 pi thirds. Pi thirds is again 1 half square root of 3 halves. 2 pi thirds. 2/3 is a little less than 1. So we're in quadrant 2 where it's negative positive. So it's negative x positive y. So what's the sign there? It's the positive y value, which is square root of 3 over 2. Pi, where's pi at? Where's the pi? Give me some pi. Where's pi? It's at 180. We already did that. The ordered pair is -1, 0. What's the cosine there then? -1. Yeah. And then 2 pi is coterminal with 0. And so the ordered pair is 1, comma 0. The sign there is on the x-axis, sine y height. and make sure you put equal signs in between them. Yeah. And then last but not least, because it's just random, right? 3 pi fourths is square root of 2 halves, square root of 2 halves. 3/4 puts you in quadrant 2, just short of 1 pi.
So isn't it just squared?
Well, it's some type of square root of 2 halves, but it's negative because in quadrant 2 we go left and up. So the cosine is negative there, and the sine is positive. Okay. So that's what we're doing tomorrow. Now that didn't even take 10 minutes, and
Cosine is a lot.
sine, way, right. I've never said cosine, why? It doesn't rhyme. Not even Willie Nelson can pull that off, right? It was a long weekend though, Brady. Yeah. Okay. Any questions on what we're doing tomorrow?
I mean, I also have to deal with shopping for a suit for Precal tomorrow.
Oh, nice. Suits are good to have.
Took about 2 hours. And I ate a raw pretzel during that time.
Raw.
Yeah, we went to Target. They were like selling a pretzel dog.
Dough? Yeah, it's called dough.
Apparently it was underbaked.
Underbaked.
Yeah, it was like underbaked.
Pan-
Like still
Like
dough.
cookie dough. Oh, I love cookie dough.
Yeah.
Cookie dough.
Yeah. Okay.
It was cookie dough. It had like salted pepper.
Oh, what if you made a cookie pretzel? Whoa.
Oh, wow. In the shape of your favorite suit, like spades,
Yeah.
or clubs.
Now, I couldn't go start that business.
Hearts, or diamonds. All right.
Personally, my favorite is hearts.
Hearts. Yeah, hearts are good. All right. We're starting 5.4. 5.4. My interns are teaching a lesson this Thursday, both of them too. Not to y'all, fortunately, or unfortunately, I should say. Now, I will, you know what? Maybe to y'all. The more time they get to do it, the better. I might invite them to come in and teach another class so they can do it twice. And yeah, and you can meet whoever. Which I have 2 of them. They're both doing the same thing. One can come in first period and try it. One can come in second period and try it. And then the real deal is 3rd and 5th. That's when they're being recorded and graded. So they can practice with y'all. Y'all are pretty forgiving, right? You can clap for them, make them feel good. Yeah. We'll have to see which one can make it. I have a male and a female, so I don't know. We'll see how that works. All right. But they're going to be teaching you applications of what I'm about to teach you. Okay. So we'll
Spotify apps,
Spotify apps.
applications like an app.
Oh, appetizers like
Yeah.
cheese
like
sticks.
pretzel bites.
All right, pretzel
Like
bites.
cookie dough bites.
All right. So this word here is very interesting, right? You can read it a lot of different ways, like sinusoids. I like that. Nosoids, right? But the way we read this is like a long U, sinusoids, and a long I, sinusoids. And these are going to end up being the graphs of, guess which trig functions. There's 2 of them. What? Sine for sure, and cosecant, no. Cosine, right? Because those are the only 2 that have sine in the name, right? You have sine and its complementary or cofunction cosine, which you don't know what that means just yet. They're not reciprocals of each other, but they both have the same name. Ouch, right? Sinusoids. Now remember that the definition in terms of x, y, and r is y over r for sine and x over r for cosine. These are the only 2 that have r in the denominator, okay? And r has to be greater than 0, right? So it has to be positive. So we're never dividing by 0, and these are not going to be negative because of r. Now, every other trig function doesn't have an r in the denominator. So x and y can be 0, but because these are the only 2 that have r in the denominator and r can never be 0, these ratios, these are defined for all angles. Every single angle is going to have a sine or a cosine. In other words, there will be no D and E, right? As we were practicing the other day, sometimes we said cosecant of an angle is D and E, or cotangent of an angle is D and E. You're never going to say sine or cosine of any angle is D and E. All right. Now, when we take these independently, what we're doing is we're unwrapping them from the unit circle, and we're still letting theta be our independent variable. But instead of going round and round and round and round and stopping, we're going to unwrap it and lay it flat on the x-axis. And so now our angles are going to run out to the right, And on the y-axis, we're going to graph what the sine value and the cosine value are. So let's go ahead and do this. We'll do this by hand. Make a table of values for theta and sine of thetas between 0 and 2 pi. Okay. Let's start by choosing quadratic angles. So whenever you want to know what a graph looks like, I think in Algebra 1 you learned this, you make a t-chart or a t-table. What'd you call them? T-table? T-chart? Yeah, okay. Less alliterative, but I'll go with it. A t-chart. And you have your independent variable on the left, and then you just plug it in, fill it out on the right, and then you plot the points, right? So let's look at our quadrature angles first. And we're going to do them in radians, okay? So 0, pi halves, pi, 3 pi halves, and then all the way to 2 pi. So those are your quadrature angles. Your independent variables you can pick, right? Whatever you want. But now the ratios depend upon those, which is your dependent variable sines. These are like your y values. So let's just do this quickly, like we're doing another practice quiz for tomorrow. What's sine of 0? 0. Good. What's sine of pi halves? 1. What's sine of pi? 0. And sine of 3 pi halves? -1. And then coming full circle, literally, what's sine of 2 pi? 0. Okay. 1, 2, 3, 4, 5. We call these the 5 critical values of sine of x or sine of theta. They're the 5 critical values because they're the quadrature angles. If I know where those values are, I can plot them and fill in between. So here's what we're going to do. Let's go ahead and give ourselves an axis over here, a y-axis. And then right through the middle, give yourself a little space on the left, but go out further on the right. Okay, now come in about right here, not quite at the very, very end. And let's call that 2 pi. Okay, so what we're doing is we're taking the unit circle. Imagine we're cutting it at the origin, and then we're just laying it flat, right? Like a piece of circle laid flat. Now, here's what's important when we start graphing these sinusoids. I'm going out to 2 pi because that's one rotation. That's once all the way around. Now, to get my other marks on your paper or iPad, wherever you're doing it, you want to try and make your scale on the x-axis the same. So bisect that distance, cut that in half physically. And you're just eyeballing it, but yours might be different from mine. And now label it. What's half of 2 pi? That's pi. And now do the same thing. What's half of pi? Well, it's about right there. And we call it 1/2 pi or pi halves. This is your quarter cycle counting interval. Remember, we did that on the unit circle on purpose so that we can count by, we split it up into like 5 pi fifths. And then we took half of 5 to get 2.5. And then we counted every 2.5 pi fifths. This is your quarter cycle interval. Now, in between pi and 2 pi halves, draw another line that bisects it. And now you're counting by pi halves. So watch this. 1 pi halves, 2 pi halves. The next one, of course, would be 3 pi halves, 4 pi halves. And now let's do this. I want to do a couple of things first. Yeah, let's go out to the next point. That would be within starting the second rotation. But now you know what the distance needs to be, right? You've established, you can even extend your x-axis. You've established what the distance needs to be in between those points. So just kind of maintain that distance by eyeballing it. And let's keep numbering it. What would come after 2 pi? 5 pi halves, and then 6 pi halves, which simplifies to 3 pi. And then I have room for one more, 7 pi halves. Okay. Now let's work to the left. If we work to the left from pi halves minus pi halves is 0. So 0 is right there. He's kind of hard to see. And then let's go back one value. I always want you to graph at least one angle to the left of the y-axis, always. What would that value be? Negative pi halves, right? We're rotating. If we were on the unit circle, we would be rotating clockwise. Okay. So again, we've cut the unit circle right there on the positive x-axis, and now we're unwrapping it. Now let's plot these points. Okay. You could do it like this. Pick a nice. I'll choose a nice contrasting color, and I'm going to make my. It's going to be pink, and it'll be a large dot. So I have 0, 0. Right, there's a point. The next half is pi halves 1. Let me go ahead and label that. Let me label that as 1. Okay. Oop, I don't want to label it like that. Let's label this as 1, and then we go down as far as -1, right? And now I can go back to putting my dots. I have pi halves 1, and then I have pi 0. Whoa, that was a little bigger. I have 0. Whoa, I forgot what thickness I was on. Oh, that'll work. And then at 3 pi halves, we have a -1. And then all the way around 2 pi, we're back to 0. Okay. And that's one rotation. I'll put the other dots here in a second, but that's one rotation right there. Okay. Now, what we could do is we could fill in the blanks. Okay. What's happening between 0 and pi halves? Well, between 0 and pi halves, my sine ratios are increasing, right? And we know why, because if you think about it, whoa, 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 big circle.
Turn it to favorite feature.
Favorite feature.
Yeah, it
Mr.
just
Corky
allows you
does
to,
it
like,
fake.
I don't have favorites.
save
He loves all his
pre-made-
students.
Yeah, it just allows you to save pre-made settings. Like you have one that's just a regular old black marker, while another's like the jumbo purple.
Okay. So let's look at what we're doing here. We're looking at the sine values. At 0, the sine is 1, right? Or the sine is 0 because it's flat. And then what happens as we rotate? Yeah, what's happening to the height of these rectangles as I rotate? They're getting bigger, right? The heights are increasing. They go from a 0 height to a maximum height of 1 when they collapse down horizontally. So that's what my y values are doing here. They're increasing, right? And then what's happening to the heights from pi halves to pi? Well, here's pi halves. Here's pi. This is -1, 0. So if we look at the heights now, what are the heights doing now as we rotate? Yeah, the heights are decreasing. Heights decreasing back down to 0. And then of course they get bigger again in magnitude, so they're becoming more negative, and then they decrease in magnitude again. They can finish the same thing. All right, so we're going to fill in these dots now. Where's my graph? Oh, right here. Okay. So how does it increase? Does it increase like this? Does it look like that? No, it doesn't. Let's go ahead and do one more value here between 0 and pi halves. We'll come over to our t-chart. Sine is a nice value when it's 1/2, right? So where is sine equal to 1/2? Is that your pi 6 or pi thirds? Pi 6. What's sine of pi 6? 1/2. Yeah. Now pi 6 is going to be right here. Pi thirds is going to be right there. Here's pi 6.
Oh, I just realized.
Now look. Yeah, Brady.
If you connect all of them in like a squiggly line like this, it kind of makes where they'd be.
Yes. That's what I'm trying to figure out. So this thing increases at a decreasing rate. Because notice, as I move from 0 to pi halves, I know my y values or sine ratios are going from 0 to 1. But already at pi 6, when I'm just like a third of the way off, I'm already halfway to the top. See that? I've made up half the vertical distance and only a third of the horizontal. And then at pi thirds, what's sine of pi thirds? Square root of 3 over 2, which is about 0.8. So now I'm about right here. So it is increasing at a decreasing rate. Boom, like that. Now, because of the symmetry in the quadrants, right? Quadrant 2, quadrant 3, quadrant 4, they're all symmetric. It's going to decrease pretty much at the same rate it was increasing. So if you draw it, it looks kind of like the Gateway Arch in St. Louis, except the Gateway Arch is not a sine graph, it's a catenary curve, which is a little bit different, but it looks the same. So there's a half rotation of sine. And now if I were to continue, it would do the same thing. It would symmetrically, it would like increase at a increasing rate and look like that. Okay. So this right here is what we call one cycle of sine of theta. One cycle, not one circle, one cycle of sine of theta. Okay. And it takes 5 critical values in order to graph it. for one cycle. One cycle in this case is once around the unit circle. Okay. What's going to happen if I were to keep going? Let's switch flavors. If I just keep going, I'm on the next rotation on the unit circle. So what would be sine of 5 pi halves? Well, it'd be the same thing as sine of pi halves. It'd be up here. What's sine of 3 pi? I'm back on the x-axis. Boom, boom. So once I get the one cycle, I can just continue the dots in this fashion. Okay, look what we're doing here. If I start at 0, 0, we call this an axis point, A for axis. It's on the x-axis. And then we hit a high point, and then we hit an axis, and then we hit a low point, and then we hit an axis. Those are the 5 critical values for one cycle of sine. Axis high, axis low, axis. We start on the axis, we finish on the axis. And now, because of the cyclical nature, the circular nature, I can just continue the graph and then turn the corner. That would be the next cycle over there. And then if I work backwards, what's sine of negative pi halves? -1, yeah, because on the unit circle, that would be rotating clockwise straight down to pi halves, which is -90 degrees as well. And that's -1. All right. So if you wanted to, you could do this. I don't know. I guess we could do this as well. You can actually trace out one cycle like this, copy it. And then if you wanted the next cycle, what could we do? We could just make a stamp and boom, there's the next cycle, right? I got too much, but you see what I mean? It's stamp, stamp, stamp. Imagine the x-axis is running by at a constant pace. Every 2 pi radians, I could take the axis high, axis low stamp and just go stamp, 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 right? And I could do that indefinitely forever and ever. And then I can actually run the tape backwards or run the table to the right, and I can go to negative land, stamp every 2 pi, stamp every 2 pi. So this is the main piece of the graph of sine of x. Now you've seen graphs like this before because it kind of looks like a sound wave, right? This is like lots of things. Travel, light wave, right? Roller coaster, up and down, up and down. All right. Yes, sir. Yeah. A hollow. Oh, a hollow. Yeah, very good. Very good. Now let's yeah, so here it is now. You can deviate from your graph and look over here. What we're doing is we're unwrapping it. And yes, there is a way to remember how to graph it. I call it sahala. Okay. Yeah, very good. So I put the S in front of a hollow. What do you think the S stands for? Sine. There you go. So to graph one cycle of sine, you need 5 critical values. That's axis high, axis low, axis. And so I call it sahala. So sine of theta now and sahala are synonymous. Okay. Now look what we do here. Because we're going to be looking at graphs of functions, they have to pass the vertical line test. F of x is what we usually name our functions. We're going to switch now from theta back to x. Are you okay with that? You'd have to be, right? You could call it f of theta equals sine of theta, but on our calculator, our independent variable, we like to call it x. So just remember that this x does represent an angle. Okay, typically in radians. Now here is your parent function. This is a new parent function. We need to know what the graph of sine of x looks like. We need to be able to sketch transformations of it as well. So the parent function is sine of x or sahala. I just call it sahala. Axis high, axis low, axis. There's one cycle. You can highlight it here. Now let's talk about some terms. Okay, let's talk about some things regarding it. Let's talk about the domain. What's the domain of this function? All real numbers, right? And those numbers represent angles, all real angles. So that's what I mentioned earlier, that sine and cosine are the only two that are defined with a hypotenuse in the denominator, which is never 0. So there's no discontinuities here. What is the range of this function? What y values does it take on? -1 to 1. Yeah. So you can say -1 less than or equal to y less than or equal to 1. Yeah, that is the radius. Or y epsilon -1 to 1. And notice I put brackets or less than or equal to's on there. we actually do reach a top value of 1. And that's when the triangles collapse down horizontally. Okay. So that's important. It stays bounded between -1 and 1. Now, because this is a wave function, that's what y'all call them, I think, in science, we can actually put a periodic wave function. A periodic function is a very important thing. A periodic function is a function like y'all that comes around at regular intervals. It repeats at every intervals. This is first period, right? So every weekday we show up at the same time. Well, kind of, right? Right, little one? Some people, right. Yeah, some people don't show up at all. But first period officially meets every weekday at 8:50, right? So a periodic function is much the same way. It repeats at regular intervals. Well, what is the definition of the period then? It's the smallest length of radians for this function to repeat its y values. And what's the period here? It says it right there. What's the period? 2 pi. Okay. And 2 pi it makes sense because that's 1 rotation, right? If I start the next rotation, I'm hitting the same quadrantal angles that are going to have the same ratios. Okay. So that's what we're going to call P. So P is the period. And we're going to define that as the length of one cycle. And for this function, the period is 2 pi. The length of one cycle. Now notice I'm calling it length. That implies x values, right? We're talking about the width now on the graph, but it's the angles. It's still angles, okay? The length of one cycle. So the period is 2 pi.
If it's the length of one cycle, does that mean it's the diameter or the radius? Or would it be
No, you can't really do that. Of the circle? No, the diameter of the circle is 2. The radius is 1, right? Okay, now again, because it's a wave function, we can start talking about some nomenclature from your science class, right? The line that goes through the center, let's go ahead and I'll use like a nice peach for that. The line that goes through the center horizontally, here it's the x-axis, right? But it's not always the x-axis. If I did a vertical shift, it's not going to be the x-axis anymore. We call this the sinusoidal. That's a great word. The sinusoidal axis. And for this function, it's at y equals 0. The sinusoidal axis is your horizontal center line. Okay? It's your horizontal center line. Now, why is that important? Well, because once you have your horizontal center line, you can actually measure the height of the wave. From the center to the top, we're going to call that A, or from the center to the bottom, we're going to call that A. Okay. A is a different A than Sahala. Okay. A is going to be your amplitude, we call it, which is the wave height. And what is our wave height? 1. Okay. You got to think of it as the height from like a calm sea. It's not 2, right? 2 would be the range from low to high. It's 2, but from the center to the top or the center to the bottom, it's 1 unit. Okay. A is the amplitude. So we have amplitude now, and we have the sinusoidal axis. And these are periodic functions. They come around. This one repeats itself every 2 pi. Okay. So remember that. What's an easy way to remember how to sketch one cycle of sine? Sahala, right? So let's go ahead and do that. Let's just practice our parent function sine. F of x equals sine of x. We're going to practice graphing it now. That'll be the last thing we do today. Sahala, right? Sahala, parent function. Give yourself an x-axis and a y-axis. All right. Now let's kind of set the table. I know it's going to go up to 1 and down to -1. I know that I'm going to come out here to 2 pi. That's the period. Half of that is pi. Half of that is pi halves. I got my quarter cycle counting interval. And now I'll bisect that and label it as 3 pi halves. And of course, I got 0. So this is what I call setting the table. We got the x and y axis all prepped. You see that? The x and y axis is all prepped. Now we're going to come in and put our critical values. For sine, it's axis, high, axis, low, axis. And all you got to do now is what? Connect the dots. Connect the dots like this. And then extend it out a little bit on both sides. We call this point right here, where it changes from concave down like a frown to concave up like a cup. We call that the inflection point. It's where the curvature changes. Well, there's your one cycle of sine. So there's your parent function. Tomorrow we're going to learn about cosine, the parent function cosine. So Sahala, today you met somebody, right? Sahala. So when I say Sahala, y'all Sahala back, right? Yeah.
Hey, can I get a Sahala?
Yeah, you can. Yeah. Hey, what did the Russian, what did the constipated Russian say when he was on the toilet? Glad to be pooping. Not Vladimir Putin. Glad to be pooping. Okay, got to get a poop joke in, right? Have a good day.